Today we will discuss about the date transform. In this presentation we will discuss what is date transform, why it is required, date transform of various functions, various properties of date transform. Date transform. The date transform is useful for the manipulation of discrete data sequence. This is very important. Date transform is only applicable for discrete data sequence. What is discrete data sequence? They are obtained by sampling continuous time signal at regular intervals. So you will get n is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is n. Okay. And has acquired a new significance in formulation analysis of discrete time systems. So understand that the transform can be used for analysis of discrete time systems. It is used extensively in the area of applied mathematics, digital signal processing, control theory, population science, and economics. These discrete models are solved with difference equation in a manner that is analogous to solving continuous models with difference equations. The role played by the date transform is in the solution of difference equation correspond to that played by the Laplace transform in solution of differential equations. We have already derived the Z transform from Laplace transform in our previous presentation. So we understand that since the Laplace transforms can be used for finding the solution of difference equations, similarly the transform can also be used for solution of difference equations. Obviously those has to be in discrete form, but in Laplace transform it is applicable for only for continuous time, and Z transform is applicable for discrete time. Now, as you can see, the difference equation as already mentioned. Let us recall what are difference equations. Linear difference equation can be written as yn plus 1 equal to yn plus t. As you can see, it is first order. Yn plus 1 equal to a yn. This is also first order. As you can see, the term yn plus 2 equal to yn plus 1 plus yn. So this is second order. Yn. This is 1, 1, 1. Sorry, this one is group. And yn plus 2 plus yn plus 1 minus 3 yn equal to n square. So do not assume that if it is n square it is second order. No, we have yn plus 2 plus yn plus 1. So it's second order. And this is yn plus 1 yn. So this is also first order. Here yn plus 1 first order, yn plus 1 yn plus 2 second order. So order is given by this term. So second order. This is second order. Highest one is 1, so first order. Okay, this is also 1, so first order. The key point from this discussion: for difference equation to be classified as linear terms of the sequence, the key point is that for difference equation to be classified as linear, the terms of the sequence yn, as I already mentioned, 1, 1, 2, 2. So 2, 2 means second order, 1, 1 means first order. Okay, arise only to the power 1, or most precisely the highest subscript term obtainable as the linear combination of lower ones. All the examples cited above are consequently linear. As already mentioned, linear difference equations. Also note that the term n square in the fourth example, does not imply non-linearity since linearity is determined by the yn terms. The yn term determines the linearity as well as the order of the equation. Now definition of Z transform, we have already derived the Z transform from the Laplace transform in our previous presentation. Let us recall once again the equation. Given a finite length signal xn, obviously it is discrete time represented by xn. If it is time domain, we write xt. This is continuous time. Discrete time means x n. Okay, n means the sample number. Okay, so Z transform of xn. Z transform xn is represented by xz given by summation n equal to 0 to infinity. This is for right hand sequence. We have considered xn un, that is right hand sequence. Xn equal to 0 to infinity xn z to the power minus n, where xn is a sequence of numbers with n all integers, n is a complex number, 0 n equal to 0 1 2 2. So as we have recalled the Z transform equations given by xn z to the power minus n for a summation n equal to 0 to infinity, wherein we have considered a right hand sequence. Right hand sequence. Obviously n starts from n 0 1 2 and so on up to infinity. Now let us consider the Z transform for some basic functions. Let us start with xn equal to 1. So if it x equal to 1, that means let us write it in terms of zxn, that is xz equals to write the formula and replace the xn by 1 and obviously zn. So we have only one term, so let us expand the zn, that is the geometric series. So if it is geometric series, obviously it will be given by the this solution 1 by 1 minus z minus 1, because this is a repeating term and consequently the powers are there. With this term is z to the power minus 1 to the power 0. This is 1, this is 2, this is 3 and so on up to infinity. So this is geometric GP. So we can give the solution as 1 by 1 minus z inverse. This is ultimately given by z minus 1. This is the solution. Now from this we can generalize it as Z transform of any constant h is given by h z1 equal to h z by z minus 1. So simply we can replace the value of h. If z1 means h equal to 1, so z by z minus 1 is similar to this one. If value of h is 2, so we write z2 equal to 2 into this transformation. So into 2. If xn equal to 2, then it will be the solution will be given by 2 into z by z minus 1 and so on. So obviously if it's a negative value, we can replace the value of h as minus 3 into z by z minus 1. Then some power series, if xn equal to a to the power n, there is a small mistake. Let us consider that this is a discrete time signal. So x in square bracket equal to a to the power n. So xn z transform xn equal to xn value is a to the power n and z to the power n. So since value of n starts from 0 to infinity, so first term will be 1, then a z inverse and so on. So this is also a GP. So the repeating term is a z to the power minus 1. So we write 1 by 1 minus a z to the power minus 1. So z by z minus a is the solution. Similarly, if value of a is 3, then you replace the value of a z by z minus 3. So z by z minus 3 and so on. If value of a is minus 3, so z minus minus 3, that is z plus 3. So this is the solution. If xn equal to n, then we place n over here. So z minus 1, then 2z to the power 2. So here this will be written as, let us take z minus common. So 1 plus 2 z plus 3z to the power minus 2, and so on. So that means we can replace 1, this is n equal to uh, um, 1, this is n equal to 2, and so on. So this is not matching. So we have to find the common term. So what is the common term? Common term is, so if you take z to the power minus 1, so it will come here, and the repeating term is z to the power minus 1. So we take z minus 1 into 1 by 1 minus z minus 1. So this comes out to be, this is the solution. So to simplify, we can write z to the power minus 1, 1 by z minus 1 to the square, that is z by z minus 1 whole square. Let us move to the next example. Xn equal to sine a n. So you can know that if we can take either sine or cosine form. So you know that sine or cosine form can be represented in terms of e to the power j a n plus e to the power minus j a n. Let us consider that xn equal to cos a to the power cos a n. So cos a n is represented by, can be represented by in terms of e to the power j a n. This is the formula. So let us replace value of xn by this term. So this has two terms. So two terms will come, one term will come here, another term will come here. So we have to determine the transform of two terms separately. The transform of this term is given by z by z minus e to the power ja, and the second term we have z by z minus e to the power minus ja. On simplification, on simplification, the ultimate term obtained will be z square you get 2z square, and you have this negative term minus z e to the power ja minus z e to the power ja. So this is z e to the power ja plus j z e to the power minus ja. So this is similar to this one, but we have a half term over here. So we can write uh, this term is equal to this, you take z common, so z gone. So this two term is actually cos a, 2 cos a, right? And you replace it the z. So this term we get minus 2 cos minus 2z cos a. Similarly, to simplify the uh, numerator is same, so we are left with z square, this term. So further simplification we get uh, this term is similar to this one. So again we have 2z cos a. So this replaced over here. So ultimately we have 2z square minus 2z cos a, again z square minus 2 cos a plus 1. We have 2 over here, 2 over here, you take common and this cancel out. So final solution is, again you can take z common over here, z common over here. So we are left with z minus cos a, z minus cos a, z into z minus cos a divided by z square minus 2. So this is the ultimate solution. Now z transform of impulse function, it is zn as or delta n, and unit unit step response un. So if you take impulse function, the impulse function is my delta n is equal to 1 for t is equal to 0 and 0 for t not equal to 0. So 1, first term will be 1, over here 1, rest of the term will be 0. So for n equal to 1 to infinity is 0. So we are left with only 1. So that means the transform of impulse function equal to 1. Similarly, you can derive the step response for unit step function 0 to infinity. As we have already discussed in our previous class, that un is given by 1, 0 to infinity. There is a right hand sequence. So we are left with only 1. So we are left with z to the power minus n. So it is a geometric series. So this geometric series will give you 1 by 1 minus z to the power minus 1. Simplification z by z minus 1. Now properties of Z transform, linearity property you are already aware of. If you linearity property means if there are two separate function, then it can be represented by C1. We can take individual Z transform of the two function and add it up. So this is a linearity property. Time shifting property, if n xn n minus, if we know the value of xn, by time shifting property we can determine the Z transform of the delayed signal, which is delayed by n naught by z to the power of minus n naught xz. So xz is the Z transform of xn. If we know the Z transform of xn, so we simply multiply z to the power of minus n naught, that is the delayed time. Multiplication by n, if you multiply if again if the Z transform of xn is given by xz, then if you are multiplying by a term n, then the Z transform is given by minus z differential of xz. So you first have to take the differential of xz, then multiply it by minus z. Now if the power of n is 1, so if you have if you want to generalize this equation, suppose you have a power of n, then in that case again you have to take the differential of that order of that xz, and again you have to multiply minus 1 to the power that factor and z to the power. Generally you will not get problems for this very complex problem. Generally this type of problem comes. Multiplication by exponential term. See, this is there are a lot of difference. This is n, this is constant. So a to the power of n, then in that case you take the z transform of xn, where z tends to z minus a, that is xz by a. You replace the term z by xz in the equation where you get in suppose z transform of xn is xz, whatever equation you have, you simply replace the z term by z by a. And by time reversal property, if you know the transform of xn to be xz, then for uh, value of x minus n, it is x 1 by z. That is, you replace the value terms z terms by 1 by z. Then you have the convolution property. You see this is a multiplication sign, still not multiplication. This is called convolution. This is called convolution given by x1z dot x2z. That means each term should be multiplied in the place values by shifting each term by a factor of t minus 1. We will discuss the convolution property in detail in our next class. Then you have initial value theorem and final value theorem. Initial value theorem is given by xz, limit z tends to infinity of xz, and final value theorem given by x infinity, limit z tends to 1 xz. X infinity given by limit z tends to 1 z minus 1 xz. This is very important. Here is no multiplying factor, but here you have a multiplying factor of z minus 1. Now initial value theorem is used to find the initial value of signal without taking inverse z transform, whereas final value theorem to find the final value of the signal without taking inverse z transform. These two properties are very important.